All right, so this is gonna be the first lecture. In the previous class, we just talked about the syllabus and the structure of the class. And this is a more technical introduction into the class. In here, this is a diagram that I pulled out from the textbook. And it kind of outlines the type of quantum algorithms that are well understood. And this is something that this is essentially one of our goals for the term, to try to understand this diagram and go into the algorithms. And in particular, quantum random walks, the application, are for quantum search algorithms. So they're a more general way to do quantum search algorithms. And Fourier transforms are also applicable. And in here, the one thing that I'll remark right from the get-go is that quantum algorithms, so first of all, quantum algorithms are not a solution for everything. They are just a solution for certain specific problems. And depending on the problems, they have different speedups. For instance, the most popular algorithm is for factoring, and that's the one that was discovered in the 90s. And that has exponential speedup, and that has a very large speedup. And for quantum search algorithm, we have some algorithms. And in this case, the speedup is actually just quadratic instead of exponential. So it's not as good as factoring, but it is an improvement. And we'll discuss this. Well, the goal is to get to this. And before we get into it, in this lecture, I actually want to go through a specific example of the difference between classical and quantum, and how quantum differs from the classical case. And this example that I'm taking from is from this book, QED, by Richard Feynman. QED stands for Quantum Electrodynamics. And this is it's a fun book. It's for the layman, and it's not that long, and it's written very well to understand some of this phenomenon of quantum theory and light. So I want to go through a specific example of this. And in general, this is what I like to do. I like to read a lot of pop sci books, a lot of pop physics books, to just kind of build some intuition or build some imagination. And I think a lot of good math and science starts from imagination. And I found this particular example fairly compelling. So this is going to be the setup. In the book, Richard Feynman goes through it in more detail. But in here, let me just tell you basically what's going on. We have a light source right here, and it's shooting some light into a glass. And in the glass, some light passes through. So you can think of it as a window. But there's going to be a portion of the light that gets reflected. And here we have two detectors, A and B. So in detector B, we detect 96% of the light that was emitted originally. And in detector A, we detect 4% of the light that was emitted. And so we have some reflection happening through this setup. And the main question here is, what happens when we put another layer of glass beneath? How much light are we going to detect in detector A? So remember that for one layer of glass, we have 4% reflection. If we put two, how much will be reflected for two layers of glass? So this is a question for you to think about. I'll give you a few minutes to think about it. And I've given some multiple choice, 8%, 4%, 16%, 0%. Think about it for a minute. When you're thinking about this, try to think about a mechanism that will give you the answer. A physical mechanism.
Will the light be reflected from one direction?
Well, the way that I have it set up here, I have the light that gets reflected here, and then the light that passes and gets reflected again.
So the reflected light from the second glass can go through the first glass?
Yeah. So maybe I see what you're getting to. So it could go like this, and then like this, like this, like this, and like this. So yeah, that's a possibility. But in here, I'm just thinking about the leading term effect. So as it starts bouncing, it gets smaller. So I'm just thinking about the leading term. But that's a good point. And you can actually like carry out the computation to do that. But I'm just thinking about the leading term. So this is a better way to phrase it would be approximately. All right, has everyone formed their opinion? Need any more time? Raise your hand if you think it's A. Don't be shy. All right, we have 8%. Raise your hand if you think it's 4%. 1, 2, 3, 4, 5. All right, 5. Raise your hand if you think it's 16%. 0. Raise your hand if you think it's 0%. 0. And I guess we need an undecided category. Raise your hand if you're undecided. 1, 2, 3, 4. 4? Was this? What's that? All right, 2. All right. It doesn't seem like it adds up to a number of people in the classroom, but we'll take it. Now, turn to your neighbor and try to figure out what the answer is. And we'll come back to it. Try to convince yourself for one.
That's the thing, I'm having an issue. I was thinking that it might not be. It's how I feel like but I'm not sure I have this one.
Assuming that there's no sort of there's no assumption of like here.
Yeah, okay, this is first.
So we just have the same reflective
That's the only one.
I'm not looking down. Yeah, I know.
But would you expect as much as 8%? I would expect it
Yeah, I feel like
it's like it's common.
I feel like there's something I yeah, that's something. That's kind of what it does.
That makes sense.
He keeps like
Yeah, I would.
All right. Let's now let's take the temperature again. We'll go through the options and see if people have changed their mind. All right, A. Who thinks A? 1, 2, 3, 4. All right, B. 1, 2, 3, 4, 5, 6, 7, 8, 9. C. 0. D. 0. And undecided? All right, 0. So we have more mass now. Does anyone want to share the mechanism that they think is happening here to give either A or B? Ben, come in.
So from a physics perspective, since we have two layers of, if they're the same sort of glass, two layers directly in contact with each other, we're not changing index refraction as we cross from the first layer back to the second. And so there wouldn't, at least in an idealized sense, there wouldn't be any reflection at that interface. It's sort of like having just one chunk of glass away.
So you're saying that all the contribution comes from this?
Yeah.
All contribution and 0 contribution. So this is going to lead to 4%. So there's nothing. Anyone else want to share anything else?
So if you use a different type of glass, the second one, that can reflect even more.
Yeah, that will change things up for sure. But yeah. In here I didn't state it, but I'm assuming a different type of glass. So, and then there's another mechanism out there, the one that was introduced classically in the book, which is that the light is traveling in waves. So this is the light from the first reflection. And then the other light, let's do this. And then you could potentially have, duplicate. You have the light from the second reflection. And classically, what one would expect is that due to the thickness of the glass, there's going to be a phase shift on the light, on the wave. And then in here, then you will have some constructive or deconstructive. And if it's one possibility, if with the right thickness, is if you match the lows with the highs, is that this too could give you 0, that the waves can cancel each other. But that's so, and you can go But you could also like pick the right thickness so that both the highs are with each other, and then you can double it that way. So now, classically, if you use wave theory that way, you could see 4%, you could see 8% if you have constructive, if the faces are the same. If the faces are different, are 0, then you can go anywhere from 0 to 8. But it turns out that depending on the thickness, you can have any of these, including 16%. So it depends on the thickness of the glass. And it's not explained classically by this picture. It's explained by quantum mechanics. So this is what I'm going to show, how using quantum electrodynamics, you can actually get up to 16% reflection, which is more than adding 4% plus 4%. So in here we need the rules of quantum electrodynamics. And in here, let me just set up the basic idea, distill the basic idea. And we're gonna represent light, a photon, by a vector B. And it's gonna be a vector in the complex plane. So it's gonna have an angle and a magnitude. And the magnitude is gonna be the probability of detecting the light. And in our case, when we have this source and this detector, we have the light coming from the source, which is our original photon. It gets split up into two vectors. One that goes to the detector A and one that goes to detector B. And originally, the length of the light at the source is 1, because that's the full magnitude. And then when we get to detector A, it's 4%. So the length of the vector is going to be, the length squared is going to be 0.04, and the length of the vector at A is 0.2. And the length at the vector B is square root of 96. What's that? Off the top of my head, I don't know. But that's not a perfect square, is it? No. So anyway, you have some that's going here. But what we care about is the light that goes into detector A. So far, so good? That's the idea. So that's the interpretation of the length of the vector. And we're representing the light as vectors. And the magnitude squared is going to give us the probability. And then additionally, there's this angle for the light vector that rotates. And theta is what's called the phase of the vector. And it's similar to the phase of the waves that we were looking before. And this theta is going to rotate at a constant rate in time. And at a constant rate in time, and light is traveling at a constant speed, at the speed of light. So it's rotating at a constant rate with respect to time and with respect to space. So, for instance, the change in the phase is going to be 36,000 revolutions per inch for red light. So this is the frequency that tells you what color you see. So this frequency is going to determine blue versus red and stuff like this speed. So this is going to be the phase angle. This is how you determine by the frequency. Now, going back to the setup, we're going to have, there's an additional rule, which I don't know how to precisely describe it, but what happens is that the orientation of the vector gets flipped in the second reflection. So if we have a vector here that comes out this way, after it gets reflected in the second one, it's going to get reflected and it's going to change the orientation. It's going to get flipped. And so what that amounts to is that we're going to have this vector of this
reflection that's gonna be made up of the detected at the source A. It's gonna be made up of two vectors, one coming from the first reflection and the second one coming from the second reflection. And the minus sign is denoting that the vector gets flipped in the second reflection. And now this alpha here is actually this. This is my alpha. And my vector is going to be this, the magnitude times the phase in the complex plane. So this is a two-dimensional vector. Does that make sense? We have this corresponds to with magnitude alpha. Oh, no. So in here, we have, what I'm denoting here is that we go through this path, this reflection, and alpha is going to be my coefficient of reflection, and theta is going to be how much the phase angle has shifted in this whole path. And in here, that's for the first path, for the first reflection. And then in the second reflection, I am going to have the same coefficient of reflection, alpha, but the phase is going to have a different change. In here, I'm actually really assuming that the source and A are really close to each other, so that it doesn't have any difference, and the difference in the path lengths, the difference between the length of this path and the length of this path, is really just given by this delta x. If the two sources and detectors are right on top of each other, then the difference of the path is just going to be given by the thickness in the glass, delta x. So then when I look at the phase of the second reflection, I have theta, which is coming from the original path. I have pi, which gives me this -1. And then I have phi times delta x. Phi is going to be my constant rate of revolutions. So I'm thinking here, yeah, it's never mind. This should be, or this should be equal to phi. Whatever my light source is, it's going to be, or the color of my light is going to have a specific phi. For red light, it's going to be this phi. For blue light, it's going to be something else. But depending on that phi, we have that the difference in the phases is going to be equal to this. Phi times delta x. Does that make sense? So the goal again is to compute how much light we're going to detect, the reflection. And again, the amount that we're going to measure is going to be the norm square of the vector. So this is, in here, if we have two sources, or if we have two possible paths, this one and this one, then we're going to have to take the norm square of this. So we're taking the norm square of this. Taking the norm square of this, the coefficient alpha comes out and then we're left, and then I also comes out, what also comes out is the e to the I theta squared, but e to the I theta is equal to 1. The absolute value of e to the I theta is equal to 1, so this is equal to 1 squared. So in here, the effect is alpha squared times 1 plus e to the I pi plus phi delta x. And now we have that this is going to be the amount that we're reflected. Yeah.
Should that 1 plus e to the I by delta x be squared as well?
Yeah.
That's a good catch.
And so we have now, we can analyze this, and we see that 1 minus cosine phi delta x, the absolute value of this, what's the minimum that this could be? 0. And what's the maximum that this could be? 2. So this I have an extra factor of 2. Where does that come from? E to the I cosine. Let's see. Let's do it live. We want this computation. This for copy. Paste. All right, so e to the I, I'm gonna call it epsilon. 1 plus, or I'm gonna call it omega. This is 1 plus cosine omega plus I sine omega. And then we're taking the norm squared of this. And this is going to be 1 plus cosine omega squared plus sine square omega. This is going to be 1 plus 2 cosine omega plus cosine squared omega plus sine squared omega. And then this adds up to 1. So we have 2 plus 2 cosine omega. So this is 2, 1 plus cosine omega. So this is actually just 2 times 1 plus cosine, and this is phi of delta x. So actually there's no square. You almost got me.
Actually, I only asked about the first square, I didn't ask about the second.
Yeah, well, I got myself then. I got myself. So it's actually, yeah. So now we see that 1 minus cosine phi delta x, the minimum is 0, and the maximum is 0. So what we get in the end is that the minimum of the norm squared is going to be VA squared is going to be 0, and the maximum is going to be 4 alpha squared. And this is going to be 4 times 0.04. So this is gonna be 0.16. So we're gonna get a reflection that's higher than the sum of the two. And this is predicted using this quantum theory. Another breath mint or Ricola. I told you guys that I'm gonna put this videos on YouTube, and I'm trying to get Ricola to sponsor me. This is gonna be the perfect example. So yeah, this is what happens, and this is the graph. And this is taken from the book. And in here, we have a graph of how much is reflected based on thickness. And the dark line is gonna be how much is reflected for the red wavelength. And oscillates this. Because if you recall, it's phi times delta x. So phi is gonna be the frequency of your light, and depending on that, that's gonna determine the thickness of this 1 minus cosine phi delta x. And the thickness here is really delta x. And based on phi, you're gonna have this two different waves. So this is for red, and this is for blue. So in this, additionally, in this plot and graph, they're looking at what happens when you actually have two types of sources, red light and blue light, happening at the same time. If you shoot them at the same thickness, then in here, depending on the thickness, you're gonna see a bluish red if you have the mixture of twos being reflected. And then in here, where the blue is 0, you're just gonna see red being reflected. And then when the red is 0, you're just gonna see the blue reflected. And then the colors are gonna start mixing based on the thickness. And here, both of them are high, and you're gonna see violet, and they're gonna mix completely. You're gonna go back to blue. This is a dim violet, reddish blue, violet, and then here, in this position where neither of them are reflected, you'll see black. So this is what's gonna happen for mixing two different types of sources of light. And you see that the probability fluctuates from 0 to 16%. So again, part of the goal in here of this lecture is to try to give you a brief introduction of how quantum theory can have a completely different prediction than classical theory. And this is something that is experimentally verifiable. You can actually have a thickness of glass, and you can actually shoot light, and you can see this type of percentage. This is to really motivate that quantum theory does predict phenomena in nature. It's not just a made up theory, because as we go through it, it's not necessarily intuitive, and it may seem a little bit abstract and arbitrary, but using the theory of quantum, we can actually predict things that happen in nature. Now, going back to the cover of the book, this is actually the phenomenon that happens in the reflection from an oil spill. And most of you have probably seen this before, and this is the image in the front of the book. In the reflection from an oil spill, you have reflections from the top layer and the bottom layer of your oil spill. And in your oil spill, the thickness varies, fluctuates, or changes depending on the position. It changes ever so slightly, but the delta X is different depending on the region on your oil spill, and it leads to this funky kind of patterns of different colors. And it's due to this type of reflection and light. So even without fancy equipment, you can actually see quantum happening in real life, and you'll create patterns like this. So for me, this is a powerful example of quantum, and this is just a brief introduction of how things are different. Any questions at this point? Yeah.
So can we not explain why the oil spill makes those colors without quantum mechanics?
No. I mean, one potential explanation would be these waves that come in and out of phase. And that might lead to something like this, but it would lead to a different diagram, a different pattern. And in particular, the strength of the reflection is not predicted by the classical wave theory. So, what's the key takeaway? So, the main difference in quantum systems is that due to this phase shift, we have constructive and deconstructive interactions between different paths. And this is going to lead to interference patterns, these patterns of different colors, and this type of oil spill patterns. And this is something that doesn't happen in classically. Perhaps using the theory of waves, you can kind of see this. But when really I think about the classical case, I think of probability theory. And that's what I take for contrast. In probability theory, we have this axiom of countable additivity. And it says that the probability of an event is equal to the probability of all the outcomes in that event. So you have an event E, and the outcome is X, and the probability of each outcome is between 0 and 1. These are all positive numbers. These are all adding constructively. When we looked at the scenario of the light, and we had these two layers. We had the source and the detector. We were looking at the specific event that the light got from S to A. And we considered two specific outcomes where that could happen. And we did V of A is going to be equal to VA1 minus VA2. So the outcome that the event that we were interested in is the event of getting light from here to here. And it was made up of two different outcomes. The outcome that it goes this way or this way. And in the quantum case, we had a destructive and constructive phenomenon based on the phase shift. And in the classical, which for me I really think probabilistic case, if you have two different outcomes, they only add constructively because they're all between 0 and 1. You don't have negative numbers to have destructive interference. So this is one of the main key takeaways that's different from classical probability and quantum probability. quantum random walks. So this is going to have a profound effect of the phenomena that we see in random systems in quantum mechanics. So I'm going to wrap up now. Next lecture, we're going to start discussing in more detail the postulates of quantum mechanics. We're going to make everything more precise. We were just kind of loosely going through an example. We want to essentially make this all mathematically rigorous. I just kind of motivated what was happening, but we actually want to be very precise. And after that, the two main phenomena that happen in the quantum case are interference and entanglement. And we'll see that interference plays an important role in quantum random walks. And we'll explore this through quantum spin systems. And entanglement plays an important role for quantum algorithms. And the first example that we'll think about is quantum teleportation. And this is related to that article that I shared at the beginning and that you can find in Slack. And the goal initially is to build basic understanding of quantum mechanics and try to understand these two phenomena, interference and entanglement. The sneak peek for the interference is these two cases. These are two plots, classical versus quantum random walks on a circle. And here we have, one of them is a quantum walk and the other one is a classical walk. And the length of the circle here is 41 and the time here is 0 to 22. Time you can see running this way. The probability goes this way and space goes this way. And here in both systems, I start the random walk in the middle of the ring and then the probability evolves. We have this one and we have this other one. Now, would you guys care to guess which one is quantum? Benjamin?
I guess the one on the left.
Left, it's quantum. And by the pigeonhole principle, this must be classical. Does anyone disagree? All right, yeah, so this is the one on the left is the quantum and the one on the right is classical. In class, we'll actually figure out how to do this exactly. This is from a spin system. And my last question is, when time goes to infinity, when it's really large, what's the probability function gonna look like for the classical case? What's that? Uniform. Yeah. Yeah, it's gonna be flat. Everything's gonna be well mixed. And what's gonna happen for the quantum case? Same? You expect uniform? So this is for time 20,000 and 20,040. So this is you also have fluctuations. The fluctuations stay even at infinite time. And this is something that's different from quantum random walks. And there is some sort of bridge between this, and this is by taking as certain limit as h bar goes to 0. And you can recover this. But it's a little subtle, but we see here briefly, this is a sneak peek of how classical versus quantum is going to be different. And in particular, you can detect where you're going to have peaks where the particle first started. So somehow you're going to retain history of the initial location. And you can see the scale here. This is flat. And the scale here goes from 0.16 to 0.02. So these fluctuations are significant. They're not very small. So this is a sneak peek into some of the things that we'll be considering
we're gonna set up the quantum theory, the postulates, so that we can start analyzing systems like this. And that's class.